Hello, welcome to this talk about a very important statistical result called the central limit theorem. We'll start by looking at a few distributions, both discrete and continuous, and then see what happens when we take samples and look at the distribution of the means. So we'll start off by thinking about discrete distributions. Now, a discrete random variable can only take certain values. So for example, if we toss 6 coins and count the number of heads, then the only possible outcomes are 0, 1, 2, 3, 4, 5 or 6. So you might be familiar with the term binomial distribution in that case, where we've got a fixed number of trials and a certain probability of success. So a discrete probability distribution assigns a number between 0 and 1, which is the probability of each outcome. And let's have a look at a couple of examples. So in the top row here, we've got two different binomial distributions. So the one on the left, we're tossing 6 coins, and they're fair coins, so there's a 50% chance of a head. And these are the probabilities of each of the different possible outcomes. And then we've got on the right a binomial distribution where we're tossing 12 coins, but this time the probability of success is 0.2. And then at the bottom I've shown two different Poisson distributions, one with a rate parameter of 1.5 on the left and one with a rate parameter of 6. So note the probabilities add up to 1. But remember, for a Poisson distribution, it goes all the way to infinity on the x-axis. Okay, let's think now about some continuous distributions. Well, a continuous random variable can take any value within an interval. It could be an infinite interval. So for example, you could have a normal distribution. You might be looking at the weights of vampire bats, for example. They might well have a normal distribution. And in this case, the probability that the random variable takes a value between two values is the area under the curve between those two values. And for discrete distributions, we said that if you add all the probabilities together, it would give you 1. An analog for a continuous distribution is that the area under the curve is 1. And here we've got some examples. So there's a normal distribution. Then we've got an exponential distribution. You might have heard of a chi-squared distribution. And then I've also included one which is a bimodal distribution. So we've got 2 peaks there. So there we are, 4 examples: normal, exponential, chi-squared, and bimodal. Right, well, if we go back to our Poisson example, here's the Poisson 1.5 distribution again. What I've done at the bottom there is I've drawn a sample from that distribution. So on the left, we've got a sample with 100, n equals 100, and on the right, we've got a sample with n equals 1,000. So at the bottom there, I've said, notice that as n increases, the histogram resembles the theoretical distribution more and more closely. And we can see the same thing with a normal distribution. So here we've got a normal distribution with mean 100 and standard deviation 10, i.e. variance 100. And we see again at the bottom, when we sample with n equals 100, it doesn't really look very much like the theoretical distribution, but when we sample with n equals 1,000, we get something that much more closely resembles the theoretical distribution in this case. Here we're considering the question of what is the distribution of the mean of lots of samples. We start with a theoretical distribution. Again, we've got a normal distribution with mean 100 and standard deviation 10, i.e. variance 100. In this next row, we see 4 samples, each of size 100, with the means calculated. We've got a mean of 99.66, a mean of 99.84, and so on. And then what we've done at the bottom is to repeat that process 10,000 times. So 10,000 times I've drawn a sample of size 100 from that normal distribution and calculated the mean. So we've got the distribution of 10,000 means of samples each with a sample size of n equals 100. And what I'd like you to notice is that again we've got a normal curve in this case, but the variance is smaller than we had in the original distribution. Okay, so what we've done there is to sample from a normal distribution repeatedly with a fixed sample size, capital N, calculate the mean of each sample, and then look at the distribution of a large number of means calculated from a large number of samples. And as we saw, we ended up with a normal curve, but the variance was smaller than the original normal distribution. And we've just got a little graphic here. We start from a normal distribution, and when we do this thing of taking the distribution of the means, we end up with a normal distribution with smaller variance. Okay, so let's suppose that instead of starting with a normal distribution, we start with a Poisson distribution. And again, I've gone back to this Poisson 1.5 distribution that we had before. So here again, we see 4 samples of size 100 with the respective means 1.22, 1.73, 1.47 and 1.6. So what distribution do the means have in this case? Would it be Poisson or would it be something else? Actually, that's a trick question. It can't possibly be Poisson because as we can see from the means there, they're not whole numbers, 1.22, 1.73 and so on. So it can't possibly be Poisson. What do we get when we have 10,000 means? Well, the answer is that again, we get something that looks like a normal curve. So what's happening here? Well, we've sampled from a Poisson distribution. That's our theoretical distribution in this case, a discrete distribution with a fixed sample size n. And then we're calculating the mean for each sample and looking at the distribution of that set of 10,000 means from that large number of samples. We've ended up with a normal curve again. And here's a little graphic. We started from Poisson, and then we've done this process of sampling repeatedly. Again, we've ended up with a normal distribution. Well, as the final example for this section, I just want to show you what happens if we start with a bimodal example. So here we've got a bimodal example, so there are 2 peaks in this particular case, and we can see when we draw the samples that again we've got some of the activity centered around 0 and some of the activity centered around 5, representing the 2 peaks of the bimodal distribution. So again, what distribution do the means have in this case? If we do it 10,000 times and we draw a sample of size 100 and calculate the mean, what distribution do the means have? Is it still bimodal or is it something else? Or maybe you're beginning to get the picture. The answer is, once again, we obtain a normal curve. So just to reiterate what we've done, our theoretical distribution was a bimodal distribution. We sampled from that distribution repeatedly with a fixed n, where our capital N was equal to 100, calculated the mean of each sample, and then again we looked at the distribution of those means. So we repeatedly sampled of size 100, did that 10,000 times, and looked at the distribution of the means. So we started from something bimodal and ended up once again with a curve that looked like a normal curve. Right, well, we've seen 3 different examples there, and I asked the question here, does this point at some underlying theory? So we had 3 different shapes. We had a normal distribution, continuous distribution, a Poisson distribution, which was an example of a discrete distribution, and also a bimodal distribution, which was continuous in this case. We repeatedly sampled with a fixed n of 100 and calculated the mean. What we found was that in all 3 cases, the distribution of the means was normal. And one question you might ask is, would it work for other distributions as well? Well, you may be beginning to suspect that indeed it would. And this thing that we're talking about, the central limit theorem, says that with a few conditions, which we're not going to go into, the answer to the question at the end of the last slide is yes. So the central limit theorem says if a set of random variables are independent and identically distributed, then the distribution of the means of samples of fixed size tends to a normal distribution. So let's just consider a little bit more of the mathematical detail behind what's going on here. So I'm going to use capital X1, X2, all the way up to Xn to represent random variables. And suppose that our set of n random variables are independent and identically distributed. Well, for random variables, we can calculate the expectation and the variance of those random variables. So I'm going to use the Greek symbol mu to represent the expectation of one of those random variables. And I'm going to use the symbol sigma squared to represent the variance of one of those random variables. Then the central limit theorem says if we add up all together n of those identically independent random variables, I'm going to call that Sn to be the sum from 1 to n of those random variables, then that quantity tends in probability to a normal distribution where the mean of that normal distribution is n times mu and the variance of that normal distribution is n times sigma squared. So that's for the sum of all of those variables. So if we want to talk about the mean, then we need to divide through by capital N. So then we can say x bar, the mean of those n random variables, tends in probability to a normal distribution where if we do the maths, we end up with a normal distribution, mean mu and variance sigma squared over n. Okay, so let's consider one more example. And we haven't done a binomial distribution yet, so we'll use that as our final example. So the scenario here is that we've got capital N random variables, each of which has a binomial distribution with parameters little n and p. Attention, capital N and little n are different. So what we're doing here is we're going to toss n coins, little n coins, and count the number of heads repeatedly. So you'll see when we get onto the numbers that I'm going to do an example where we toss 10 coins repeatedly, and then we do that 100 times. So our capital N is going to be 100. Right, you may remember that for a binomial random variable with parameters little n and p, the expectation of one of those random variables is np, and the variance of one of those random variables is n times p times 1 minus p. So if we put these into the formula that we had on the previous slide, we're going to conclude that the average x bar tends in probability to a normal distribution with mean np and variance 1 over capital N times little n times p times 1 minus p. I hope this will become clear when we actually put in the numbers on the next slide. Right, so suppose we repeatedly toss little n equals 10 coins, and there is a probability p equals 0.2 of getting a head. Let xi be the random variable corresponding to the number of heads on the ith set of 10 coins. So we've got one experiment where we we toss the coins 10 times, count the number of heads, and do that repeatedly. So we're dealing with a binomially distributed random variable with parameters 10 and 0.2. So we can very easily work out the expectation and variance of each of these random variables. Expectation is 2 and variance is 1.6. And we're going to suppose that each run of the experiment, we toss the 10 coins a total of capital N equals 100 times in this case. So in the top here, we can see the theoretical distribution for a binomial distribution where we toss 10 coins and the probability of a head, probability of a success is 0.2. And again, I've shown you 4 samples there where we've taken n equals 100. As we said, for each of our random variables, there's an expectation of 2, a variance of 1.6, and our capital N in this case is the sample size. So capital N equals 100. So we're now in a position to work out exactly what the distribution of the mean is in this case. So we know that the distribution of the mean is normal with mean 2 and variance 1.6 over 100. So what we see in the bottom of this slide is first a histogram showing the distribution of 10,000 means. And then on the right-hand side, we've got the theoretical distribution that we've just shown on the left. So mean 2 and variance 0.016. And you can see there's a pretty good fit. There's a little bit of wiggle on that histogram on the left, but basically that's a really good theoretical fit to what we've seen there. So just to conclude, to reiterate what I've said before, the central limit theorem states that if a set of random variables are independent and identically distributed, then the distribution of the means of samples of fixed size tends to a normal distribution. And in the little graphic at the bottom here, we see 3 examples of continuous distributions. So I've done a normal mu sigma squared, a bimodal one, and an exponential with some parameter lambda. And then on the right, we've got a couple of discrete distributions, Poisson with rate parameter mu, or a binomial with parameters n and p. So irrespective of what distribution we start with, when we apply this process of repeatedly taking samples of a fixed size, calculating the means, and looking at the distribution of the means, it's always going to be a normal distribution. Thank you very much.